Okay, so we'll now move from De Morgan's to commutativity. So De Morgan's is a difficult rule to remember with all the tildes and dots and wedges and so forth. But hopefully commutativity will make up for that because it's quite simple. Basically, just note how these mean the same thing, right? Warren or Rubio will win means the same thing as Rubio or Warren will win. Bush and McCain are Republicans means the same thing as McCain and Bush are Republicans. So, formally speaking, what we're talking about here is that P wedge Q means the same thing as Q wedge P. And P dot Q means the same thing as Q dot P. So, you don't even really have to think about that. All you need to remember here for commutativity is that when you have a wedge or a dot, what this rule tells us is that we can spin those pieces around, okay? They spin around with no problem because they mean the same thing. They're replaceable by one another, and that's how we can use the rule of commutativity. And the rule of commutativity is a useful one. Oftentimes it will come up in the context of, as I was indicating in the previous video, if you have A dot B, you can do commutativity on that in order to get B dot A, which now enables you to get B by simplification. And of course, we already know we can get A by simplification. And so what commutativity allows us to do is take an A dot B, simplify and comm and simplify so you can get both pieces laid out. And that can be very useful in terms of doing all kinds of proofs, okay? So yeah, you will hopefully get used to using commutativity quite a bit. Now, two other rules here I want to talk about, replacement rule-wise, and then we'll get to our last one for this video, or this sequence in 6.3. But that would be associativity and distribution. All right. This was COM. Associativity, I think this pen is quite up to the task. Okay, so associativity here has a couple versions. And as you can see here, by the way, I don't have written out examples here. So I'm going to go ahead and move this out of the way so you can see me. And then I'll just relate that information there to you in just a second. At any rate, associativity says when you have P.Q.R, you can slide the parentheses over without any consequences because, again, the statement on the left means the same thing as the statement on the right. Likewise, if they're all wedges, you can take that parenthesis and, again, move it over without any consequences because it means the same thing. Now, in terms of illustrating this, right, we could say, for example, let's say over here I have a bag, and inside of it I have my lunch, right? And I tell you that for lunch today, I have an apple and a banana and an orange. Now, that would mean the same thing as if I said, in my lunch, in my bag today, I have for lunch an apple and a banana and an orange. Right? I just paused in a different location here in each of these sayings of the statement. But it means the same thing. There's no difference in the calories. There's no difference in the food. Talking about an apple, a banana, and an orange. Whether the parentheses are on the right or the left, it means the same thing. And we just understand, though, that we do need the parentheses, as we talked about in 5.1, because we always have to define or have a main operator identified. And so here on the left-hand side, it would be the left-hand dot. Here it would be the right-hand dot. Again, logically speaking, though, they have exactly the same meaning, though where the main operator is might be a little bit different. The same thing is true here down with when we use the wedge, P wedge, Q wedge R. So if I told you I have in my bag for lunch today an apple or a banana or an orange, well, that would mean the same thing as if I told you for lunch today I have an apple or a banana or an orange. Again, the only adjustment I made there was in terms of where I pause. Do I pause here after the first item or after the second item? Logically speaking, it has the same meaning. We can move those parentheses all around as much as we would want to. Now, Distribution is a similar rule, or at least looks similar. Two versions of this rule as well. All right. So two versions of the rule of distribution. They obviously look similar, associativity and distribution. But note here, associativity has all dots or all wedges, whereas distribution has a dot and a wedge in each case, some of both, in other words. And so in terms of keeping these straight, because that is one of the challenges of this course, and that is keeping the rules' names straight in terms of which name goes with which rule, I would put it like this, or I would encourage you to think of it like this. Associativity, right, begins with the letter A for all, as we know, A for all dots or all wedges. Associativity, A, all dots or all wedges. Distribution, of course, begins with the letter D. D is in different. Different operators, dot and wedge, different. So they look very similar to one another, but if you can think of associativity and all, so all dots or all wedges, that will hopefully help you keep it straight from distribution with its D for different. Now, how can I explain how distribution works? Let's see here. I could start at the bottom one, actually, with the lunch example. So let's say I told you I had in my bag for lunch today an apple or a banana and an orange. I forget which one, right? I have an apple or I have a banana and an orange. Actually, I don't want to use the lunch example on that one. That's a little bit complicated. I'll come back to that one. I'll say I told you I have an apple and a banana or an orange. Well, that means, right, that I have an apple and a banana, or I have an apple and an orange. That's what this statement means. To say I have an apple and a banana or an orange means I have an apple and a banana, or I have an apple and an orange. So I hope that makes it help you see how it makes sense to say the statement on the left means the same thing as the statement on the right. In the lower example here, the lunch example, is why I hesitated there, doesn't work as well. So let's say that I am in downtown Seattle, and I tell you to come and meet me. You're in Linwood. I'm in downtown Seattle. And I say, come and meet me here, but I only want you to take interstate freeways to do so. Well, you would know then that to get to downtown Seattle from Linwood, let's draw a picture here. You could take I-5. But sometimes bad things happen on I-5, right? Sometimes there's a crash or there's traffic or whatever. And in that case, it might make more sense to take I-405 and I-90. Again, remembering that we're going to be limited to interstate freeways. So if you show up in downtown Seattle from Linwood, right, this is what I would know. You took I-5 or you took 405 and 90, right? That describes the scenario here. So if you show up in downtown Seattle, I would know two things. You took 5 or 405, and you took 5 or 90, right? Both of those things would be true. Show up in downtown Seattle from Linwood. So that's how associativity and distribution work. They don't come up all that often. As you can see, there are a lot of moving parts here, but they can be useful. I would say particularly distribution, right? Because, for example, here, this statement here we're just going over, the main operator here of this statement on the left is the wedge, right? But there are not a lot of things you can do with a wedge. But if you apply distribution on it, in other words, if you distribute, hence the name, the P to both the Q and the R, the wedge there turns to the dot as the main operator now on the right-hand side. And once you have a dot as a main operator, things start to look better, right? Because you can simp, and then we'll be able to com, now that we have commutativity, and then simp that as well, and get these two pieces and do things with those. So do be prepared to use distribution, but you'll need to look for that pattern of dots and wedges to be able to pull that off. And of course, if you're going from right to left here, you need to have exactly the same thing in these two positions in order to suck them together, so to speak, to put them out there to pull off distribution. Okay?